Good afternoon, everyone. I'm Moftakhari, the Faculty of Civil Engineering at UA. And I first thank you all for being around on Friday before the spring break, and the afternoon of Friday. And I'm not going to compete against those pizzas, so enjoy your time. Feel free to ignore me. So, what I'm presenting today is not my own product. It's a community effort of a larger group. I'm presenting on behalf of those people, PhD students, postdocs, affiliates with the Center for Complex Hydro System Research. We have a lot of research ongoing. And if in some cases I'm missing some of those citations because many of these works are already under review and revisions. So if there's no citation next to it, that doesn't mean that I produced myself. It's just collaborative work. But so don't be picky on those. The title of my talk is Challenges for Compound, like Challenges and Opportunities for Multi-Hazard Risk Modeling in a Changing Climate. So there are a lot of terms here that I'm going to walk you through the definitions step by step and help you get more familiar with my research. And so, of course, like 20 minutes or so is not sufficient to cover every single detail, but I'll try to keep it educational enough so everybody gets familiar, and that would be more of an opening to follow-up discussions than wrapping up whatever I'm going to do and I've done before. So let's start with a recent event. Hurricane Ian in September and early October 2022 hit the coast of the United States, first made two landfalls, one in Florida, one in Carolinas. And so an overall of like 148 deaths been reported, around 120 related to water. And keep this number in mind because this is very important, because we usually characterize the hurricanes by their wind intensity, not flood intensity. But you see that we are losing much more to floods than winds. Now this is one lesson to keep in mind, that we already miscommunicating the risk. So, and also if you look at the damage, like $67 billion damage estimated, and it's already made into the top 5 hurricanes in the history of the United States. Well, just 1 year ago, just 1 year before that, in August and early September 2021, Hurricane Ida hit the coast of the United States. So, are we experiencing these too frequently? Probably yes. Because if you look at, like in year 2021, there were 20 separate billion-dollar weather and climate disasters. And many of those, including the names that you see down here, are hurricanes and tornadoes. And we are losing billions of dollars almost every year beside the unfortunate casualties associated with these. So if you look at the history of most expensive weather and climate disasters in the United States, probably you see what I'm seeing here too, that the number of hurricanes and tropical cyclones that causing damage and death are increasing. So the numbers are increasing, not necessarily because the intensities are increasing. Probably one reason is that, as Ivy already mentioned, we are building and developing in those high-risk areas because those are coastal regions. Those are good places to develop. And also it can be attributed to climate. So I'm not here to attribute it to one versus another, but probably a combination of all these reasons. Now the question is that, if you're losing a lot to these, what is wrong with our risk characterization and decision making? So Abby already did a really neat job on going through the layers of decision making. Now I'm going to focus more on the flood inundation mapping and hazard aspect of the problem itself. If we are going to look into them, like this is a picture from the Hurricane Harvey near Houston downtown. And if you look at the report that National Academies of Science published after this hurricane in 2018, look at this sentence. Approximately half of the homes in Houston affected by flooding from Hurricane Harvey were outside the map floodplain. So this means probably we are failing to generate effective and useful flood maps. And depending on how we characterize the floods and how we guide those flood efforts to generate flood maps, probably we need a deeper look into this and see how we are generating it and whether if it's compatible with the nature of floods.
What if the event was larger than just 100-year event?
So I will talk about the details, but the one main message is that this is not the only event, but in many of these cases, this is an example that those flood maps are not necessarily the most effective way to let the people, whether if they're at risk or not. That's an extreme example, of course. So here, when you look at the guidelines that we have in the United States for flood mapping and flood risk characterization from NOAA Class 14 all the way to FEMA guidelines or Bulletin 17C, like this one is for river flooding, this is for coastal flooding, and this is for like frequency of rainfall. One evident shortcoming is that we are designing to flood drivers in isolation. In Bulletin 17C, there is no discussion of coastal flooding, and in NOAA Class 14, there is no discussion of coastal condition. And so, if, getting back to the hurricanes, which we are going to talk about them more, it's a combination, it's a coincidence of coastal flooding due to strong wind and inland flooding due to intense rainfall. So, are we missing some very important stuff? That's the main core area of my research. So I'm focusing on two different aspects of multi-hazard risk assessment, especially under changing climate. First is multivariability or compounding effects. Once you have multiple interrelated and interactive variables involved, you need to come up with appropriate tools to characterize them. Second is that we are dealing with non-stationarity. We are dealing with land cover land use change, sea level rise, climate change, all those effects that are going to contribute to the intensity of floods. But what we do, based on those guidelines that I just showed you, we are designing to a stationary system. So in those equations, none of those parameters are time variant. So what are the solutions and what are the challenges? Here I'm showcasing one example of how these two effects are going to affect the design implications and how we basically mischaracterizing the risk and how we communicating the risk. So before doing that, I'm going to get into the definition of compound floods in more depth and more technical term. If you refer to, there are not many definitions out there, but if you refer to IPCC, it's a two or more simultaneous or successive extreme events, or combination of extreme events that with underlying conditions that amplify the impacts, or combination of events that are not themselves extreme, but the combination leads to some extreme impacts. One quick example is that this is a coastal community that the drainage system has been designed good enough to convey a runoff generated after design rainfall, like a 25-year rainfall. But what happens if that same rainfall happens during the time that the outlet is already blocked due to elevated sea level? So this elevated coastal water level is not going to flood the community because the seawall is high enough, and the drainage is supposed to work well enough under that rainfall. But what happens if these two coincide? That's what we call compound flooding. And so if we look at more in depth into the various forms that this compounding are going to happen, let's looking into flood forcing phenomena. Let's focus on like hurricanes. During hurricanes, we have terrestrial regime due to torrential rainfall that happens over the coastal watershed and the generated runoff going towards the coast. At the same time, we are having the coastal elevated sea level due to storm surge. And these two are going to combine and leave the community flooded, as you see here, or in other forms of combination. So, probability 101. If we are going to design and characterize the risk or hazard associated with that from a probabilistic perspective, if we are using, as it is already recommended in all those guidelines, to focus on univariate metrics, what we do basically we take the time series, we calculate the probability density functions, cumulative distribution functions, focus on a specific CDF associated with the design return period, and we take this discharge. If we have a good HEC-RAS model or any other forms of hydrodynamics model, that would be the boundary proportion that we put in, and we use that information for flood risk assessment. So we were going to have, if you have a 50-year design scenario, that would be the discharge for a design. But what happens if you are having multiple variables involved? That means besides considering each of those variables involved, that individually that we call the marginal distributions, we need to also look into the correlation structure in between. And so develop this some level of curves of PDF and CDF, and now instead of just one scenario here, an infinite combination of, let's say, coastal sea level and rainfall on both axes is going to give you a combination of drivers that are going to give you the same return period of 50 years. So here, infinite combination of these would have the same compound return period. That's the challenge that we need to tackle. I'm not going to get into the details of how we're formulating it, but I'm just trying to highlight the challenges that we have from technical perspective. So the challenge is that, again, probability 101, probability of A and B is some form of conditional probability. That would be probability of A given B times the probability of B. And if those events are independent, we can assume that the probability of A given B is simply the probability of A. That means the probability of A and B is simply the product of marginals. Easy. But what happens if there is a statistically significant dependence between variables? That means that probability of A and B is no longer the product of univariate probabilities. You need to go take a step forward and model it through joint probabilities. And so one very effective tools that we usually do in these cases are a couple of functions, which are joint probabilities, joint probability functions. I'm not going to get into the details, but I'm offering a course in fall semesters in environmental data analysis. There are lectures on this, and I would encourage you to take if you're interested in that. But getting back to the challenges that we have from the design implications perspective. These are the time series of variables that might contribute to the flooding around Houston and Galveston Bay. So look at the time series of river discharge fluxing into river discharge, local precipitation, which we call the fluvial, pluvial, and coastal, three various sources of flooding that contribute to the flooding around Galveston Bay and near Houston. If you look at these drivers, if you split the record into like two somehow overlapping records, and you fit the distribution like a GEV distribution for this calculation of design, you will see that it's already, even without looking at the compounding effects, you will see a shift in the distributions. This is Buffalo bioflow, and this is the total water level. And you see that if you look at the coastal water level, it's already shifted from the historic to the current system to the right. And this change can be attributed to the sea level rise. It can be attributed to other factors that contribute to the extreme sea level. But what is evident is that these two distributions are not the same. So if you are designing to a stationary system, you are probably mischaracterizing the risk, not only for current, but also for your projections in the future. Now let's take a look into the dependency structure. As we said, it's a statistical representation of joint probability. And so here I'm plotting this matrix, plots river flow, precipitation, and coastal water level. I'm taking storm surge as a representative of extreme coastal water level. And those numbers that you see here, those are statistically significant correlation coefficients between those variables under each plot. And among these two, I've selected two of them to highlight and show you that if you calculate this rank correlation and tail correlation, which are the correlation coefficients representing the dependency of these two variables, statistically speaking, even those dependencies are not gonna, statistically speaking, have not been stationary over time. And if you look at this graph down here, since 1985 forward, you will see that in the past, like in 1980s and 1990s, it's been all mostly either insignificant or lower than most recent records. This means not only the marginals are going to change or have been changing over time, but also the correlation structure between these two might have been evolving over time as well. That's about precipitation and river flow. This is about precipitation and surge. Now the question is that what would be the design implications again? So how it's going to affect the design of our risk mitigation plans. So I divided and split the events into historic versus recent, and use the package that he developed back in 2019. It's already in GR journal if you like to take a look into it. And you see that if you split the record between two historic versus current system, you're gonna get different marginals fit and also different bivariate hazard curves, which are going to be associated with different levels of hazard. And so basically Q50 in the past has been significantly different than the current Q50. And also on the coastal side, you're gonna on the precipitation side, you will have different percentiles associated with that, and you're gonna have historic compound extreme being this combination if you focus on 50-year event versus the recent one, which is significantly different. Now the question is that are we designing efficiently to the ever evolving dependence and variability in each of these variables? These are, again, the challenges of design implications. And once we figured it out, now it's time to see. So basically, one takeaway message is that non-stationary individual flood drivers and their compounding effects that are evolving over time, if ignored, lead to underestimation of compound failure. And so after that, you can even go further and try to attribute it to some characteristics of the system. If the correlation structure between rainfall and river flow has changed, we know that one contributing factor would be the infiltration capacity and the urbanization. You look at the map on the left, and it shows how over time Houston area has been urbanized, and that intensification has happened over time. That's probably one reason that we can attribute this change in the correlation structure into that, which with the probably the same rainfall intensity, you're going to get larger river runoff being generated. Going forward and taking it to the coast a little bit, this is a map of sea level rise based on tide gauges all around the globe. And so you see that in many cases, including the Gulf Coast of the United States, we are experiencing pretty large amounts of sea level rise over time. How this sea level rise is going to help us? Basically, sea level rise is the case that we are experiencing an increase in the average water level over time. So if you look at the coastal water level, that goes up and down every day. If you take the long-term average, we call it mean sea level. And this sea level rise is simply the increase in mean sea level over time. So if you are shifting this mean fluctuation over time, that means it is very likely to get higher extremes in the future. What does it mean? Putting into formula, we usually refer to GeV functions for extreme water level frequency analysis. And this is a work that Georgios, who's here, has led that. So basically, if we condition the location parameter, which is can be directly connected to that mean of that data set, if that location is connected to the mean sea level, which is changing over time, we can try to let the distribution to change distribution parameters to evolve over time to somehow address that non-stationarity that I just talked about. Then you will be able to formulate it and come up with some estimates of the return level for a given percentile if it's for example 100-year event. What does it mean? That means if you take the current 100-year event, current 100-year coastal water level, and take into the projections of sea level rise in the future, and take it into that GeV and let it evolve over time, by 2050, you're going to have these return periods under the projected sea level rise, so which is way below 50 or 100-year event that you started with. So we can simply formulate it around a non-stationary distribution to see what would be the future of the flooding. Or in another way, this is another way of looking into the same results. What you can do, you can take a look at the 100-year return level. Currently, or based on historic record in San Diego, probably, for example, 3.5 is going to give you a 100-year event. But in the future, that's no longer a 100-year event. The 100-year event would be close to 4.5 or even larger. So if you are designing in San Diego a coastal levee to this water level for a 100-year return period, it's very likely that it's going to fail in the following decades. So these are non-stationarity that I'm talking about. And this non-stationary and sea level rise is not just about extreme floods, but also on other type of floods that we call the minor floods, sunny day floods, or nuisance floods. Another terminology that is very common in coastal flooding, it's called high tide flooding, because it's a type of flooding that happens during non-extreme events. There is no storm coming, it's just an elevated water level. And if the average of coastal water level has already risen, this fluctuation of daily water level is going to cause trouble in the community. That's what we call a nuisance flooding or high tide flooding. So these are quite examples, and there are tons of studies already out there that shows that we are expecting more frequent nuisance flooding or high tide flooding in the future. And if you would take a look at this, and like many other residents, you might say, okay, this is a few inches of water, it comes out and goes down. Why should we care about it? The problem is that if you care about those extremes, which you expect to happen once in every 50 to 100 years, these are going to happen every week, every couple of days. And so it's like drawing penny while you're walking. So you might not, at the incident level, you might not be considering much about these, but over time, if you accumulate the cost due to traffic interruptions, business interruptions, health impacts, all over time, these high tide flooding are going to be influential. So what we do and what NOAA is currently doing with regard to these high tide floodings. What is the problem? The problem is that if you look at the fluctuations, let's say if this is a time series of water level fluctuation at the point of the coast that we call it the tide gauge. Looking into this time variability, we usually come up with some high water that we expect on a daily, regular basis, and a low water, which just mean higher high water, mean lower low water. These are terminologies for coastal dynamics. So what happens currently, NOAA tries to generalize the definition, because one problem with these high tide flooding is that we don't have a threshold to say whether if high tide flooding has already happened or is going to happen or not. And this comes from continuous monitoring over the past. If the water level at the gauge goes above a certain threshold, we call it the high tide flooding. So for this, you need two things at the same time. First, you need an installed gauge with a long enough record. Second, you need a monitoring system that tells you if water level goes beyond this specific water level, the flood has already happened. And given all those conditions, we don't have many tide gauges around, even in the United States, that we have this. So NOAA came up with a solution in 2018 and said, try to find a relationship at gauges that they already have those high tide flooding, which is of course above mean high water, because this is the water level that the coastal community already expects to experience. And try to find a linear relationship between just GTR, greater tidal range, which is simply the difference between maximum and minimum. And they come up with this linear relationship, which is pretty straightforward, pretty simple. And look at the fit, that's perfect, right? It's just perfect fit that you can say, okay, wherever you know what would be the tidal variability, you can run a model. It tells you how much water going up and down, and so fit this line, plug it in, you're gonna have the threshold, boom, you don't need the record. But what happens is that if you look into depth, you will see that this high tide flooding threshold that they're measuring and they're proposing is presented above mean lower low water. And we know that this, if this mean lower low water is simply tidal range plus high tide threshold above the high water. This is the uncertain portion. This is something that we already know about the system. And so what do you do here? You basically plot GTR plus something versus GTR. That's why you get a perfect fit. And this is the manual for NOAA right now. And they have already released thresholds for elsewhere based on this relationship in 2022. And currently we're working with Billy Sweet, who is the lead author of this, to revise this approach. And so what we are doing, if you look at the statistics, these are the graphs, because Salaf is not here, so she produced this all. And so look at the skills based on that, if you do it fairly and you take the GTR out of this calculation. So it's not working. And so what we are doing, we have tried, and we get like prominent results already, that we look at the relationship between various factors that determine the sea level rise and also high tide flooding threshold. The good thing about this approach is that we can come up with a spatially distributed both sea level rise and high tide threshold, because that's a limitation that I mentioned that earlier. Like we have like 100 gauges distributed along the coast of the United States, which are not necessarily distributed everywhere. So you have a portion of coast that you don't have measurements to come up with sea level rise estimates, neither the thresholds. So using those machine learning algorithms, we came up with these sea level rise, spatially distributed sea level rise projections every 10 kilometers along the coast of the United States. And this map gives you those thresholds for nuisance flooding, spatially distributed every 10 kilometers along the coast of the United States. So these are preliminary results. We are about to submit it. Another opportunity that I'm going, so that was the opportunity that data methods like machine learning is going to provide you with. Another opportunity that I'm going to highlight here, that's a remote sensing, the opportunity that remote sensing and cloud computing is going to provide us with, and that's a project that Majid actually led that. So basically, if you look at this paper is already out there, but very briefly speaking about it, many of those remotely sensed data products are already out there, including on Google Earth Engine. And so, in this project, we came up with some method that you can easily, and the code is already available out there, so you can easily go to that link and change the boundaries, change the time, and you come up with a new flood map for yourself wherever you want. But the good thing about this is that it basically makes it easy for you without needing to download the data, without needing to go too much of like hustle of like data preparation, because many of these are already here. And so these remote sensing and cloud computing makes it much more efficient for everyone to come up with this flood mapping. I'm about to wrap it up in just 2 to 3 minutes. Another category of opportunities that we pursue in our lab is process-based modeling. So we know that there are a number of hydrodynamics models out there. These are 3 examples of the models: DFlow-FM, ADH, which is developed by Army Corps, and HEGRAS. And besides these, we have other models trying to involve them, like Schism and ATRIC. Those are other options that we consider. However, coming up with one versus another needs a good understanding of what are the limitations and differences between those models. So one project that we are currently doing is in some form of intermodal comparison to see whether about the efficiency and accuracy and other forms, whether if there is one model preferred versus another. But again, these are snapshots of 3 of those models that we are currently doing for Galveston Bay. One challenge with those process-based modeling is the boundary forcing itself, because as I said, infinite combination of boundary forcings are going to have the same return period. So if you're going to come up with a flood map of 50 years for Galveston Bay or for somewhere else, you need to run these models for like hundreds of scenarios, which is not possible. Another difficult, that's from the risk assessment perspective. Another one is for flood forecasting perspective. Let's say you're having a storm coming toward the coast, and all of you have already seen those spaghetti curves down there. That we know that many of these are possible. Basically, all of them are possible. But which one should we care about? Because we don't have sufficient time to run our computationally demanding hydrodynamics models for all those scenarios. What we came up with, Miraj led this project. We came up with a dimensional reduction approach. We call it CLI, or cumulative likelihood of impact. So what it does, it looks into the dependencies between offshore forcing. Let's focus on Galveston Bay, which is the area that we are curious about its compound flooding out of upcoming storm. So the flooding over there is going to have 2 drivers, upstream boundary condition and downstream boundary condition. What we do, we look into the offshore conditions and its dependence with the downstream boundary condition. And we also look into the inland rainfall distribution and its dependence with the upstream boundary condition. If we do that, we are going to come up with these maps that the correlation has been quantified between those drivers offshore and inland, with the flooding intensities. Then, along the path of the hurricane, what we can do, we can give points if the hurricane path goes through darker points. So, for darker points, it's going to catch more points than lighter colors. This means that storm is going to have more capacity to cause trouble and flooding. This way, among those thousands of scenarios, what we do, we come up with a handful of 10 scenarios which have already gained points along the path without even running a numerical model at all. Once we get those 10 selected storms, then we can run them in a numerical modeling framework that we've already developed, and then we can say, out of these 10, 15 runs, we're going to have the large range of possibilities, extreme possibilities out of these 6 storms that we can make decisions very quickly for flood forecast. So this is another project that is about to be submitted, and I borrowed this graph from a paper that came on, who left us last year to Princeton for postdoc, worked with David Munoz, who's already at Virginia Tech. We worked on this paper to look into how uncertainties from various sources, from terrestrial to coastal, are going to contribute to the uncertainties of compound flooding in freshwater influenced coastal systems. So in this paper, we've summarized various sources of uncertainties and how assimilating hydrologic and coastal boundary forces, which is not this data assimilation is not my area of expertise. That's what his group are doing. So we are trying to provide sufficient information for these well-coupled hydrodynamics, hydrologic models to come up with a reliable estimates of uncertainties around those flood intensities that we are predicting. So this is more or less the what we call it hybrid modes or hybrid models that would be probably the future steps to be taken in the following month through Cairo. And this is the word cloud of my research. So you see flooding, compound, sea level rise, and some other terms being around. And specifically about Cairo, I have the opportunity and pleasure to work with scientists on these 2 projects. First one is physics informed, which I'm working with Amit on physics informed machine learning for compound flood mapping, and trying to integrate what we learned about those machine learning benefits into specifically, if we have well-coupled models, how we can improve, particularly in data scarce regions where we don't have measurements. And so we have some hydrodynamics models, but those are computationally expensive to be run for every single scenario. So can we combine those process-based modeling with machine learning to come up with an efficient way of estimating flood intensities around those systems? And for Project 9, again, I have a pleasure and opportunity to work with a larger group, like Abby is there, Nate, Hamid, and Julia Cherry, and other colleagues, that we are going to take a look into the coastal nature-based solutions to mitigate flood impacts. So in that case, we couple hydrologic and hydrodynamics with an ecological response model that is going to help us quantify the response of wetlands to hydrologic, hydrodynamic conditions. And that would be involve some stakeholder engagement to receive inputs and implement all those scenarios. Thank you all for staying around, and I know I'm over time already, and I will thank the funding sources and y'all, and please, if you have any questions.